I'm going to evaluate the integral of x squared y dx minus 2xy dy along the closed curve C, where C there is a semicircle in the first and second quadrant. So the semicircle is the one that I'm drawing here, which has a radius of 2. So that semicircle there, which has the equation x squared plus y squared is equals to 4. So that's the semicircle that we are having there. So in this case, it is convenient to split the curve into two parts, which I'll call C1 and C2. So this part here, I'll call it my C1, and this part here, I'll call it my C2. So we have those curves there, C1 and C2. Then our integral along the closed curve C then becomes the integral along the curve C1 plus the integral along the curve C2. So those are the integrals that we have now. And we now go on and look at each curve. So curve C1 there, we see that it has a term which is x squared plus y squared is equals to 4, which is 2 squared. In this case, when you have terms which are of this form, it is convenient to use polar coordinates. So when you are using polar coordinates there, we are having thus an equation of a circle x squared plus y squared is equals to r squared, where the r there is the radius. So when you compare these two equations here, we see that our r is equals to 2. So in polar coordinates now, we would have our x is equals to r cosine theta. Substitute the value of r, then we have x is equals to 2 cosine theta. Then for our y is equals to r sine theta. Then substitute the value of r, then we have y is equals to 2 sine theta. Then differentiate this equation with respect to theta. Then we have the derivative of x with respect to theta is equals to minus 2 sine theta. And differentiate this with respect to theta. Then we have the derivative of y with respect to theta is equals to 2 cosine theta. So we have those derivatives there. And then we can get the dx there. It will be minus 2 sine theta and the theta. Then from the second one, we have dy there is equals to 2 cosine theta. So we have those equations here. But you just have to recall that when we measure theta, we measure it from the positive x-axis in the counterclockwise direction. So we measure it in using a graph like this one here, starting from 0 up to 2 pi. So in this case, our integral along the closed curve is in the counterclockwise direction. So we are moving from this point here, which is a 2. So when you start from that point, our theta will be starting like from this point here, it will be a 0. So we have theta is equals to 0. Then we are going to end at this point here, which is equivalent to this one here. So we'll be saying theta is equals to pi. So we are saying the theta varying from 0 to pi. So if we have theta varying from 0 to pi, and the integral along the curve C1 of x squared plus y squared dx minus 2xy dy, it will give us the integral from 0 to pi of x squared plus y squared dx minus the integral from 0 to pi of 2xy dy. But here we have that x squared plus y squared is equals to 4. So this value of 4, we substitute it on this equation here. So we put it there, it becomes a 4. And for the dx, we have the dx there is minus 2 sine theta d theta. So what we'll do is we'll substitute it here on this part. So that our integral there becomes the integral from 0 to pi of 4 times minus 2 times sine theta d theta. Then we go on and look at the next part. We are having our x there is 2 cosine theta and our y is 2 sine theta. So we'll substitute it on this part here. So what we have there is all this, we'll put them here, and our dy is minus 2 cosine theta and theta. So we'll substitute it here. And we have that our integral there is the integral from 0 to pi of 2 cosine theta times 2 sine theta times 2 cosine theta d theta. So that is what we are having now. And this part will simplify to the integral from 0 to pi of minus 8 sine theta d theta. And this part here simplifies to the integral from 0 to pi of 16 cosine squared theta sine theta d theta. So those are the integrals that we are having. We then go on and look at this part here. we integrate it. So for us to integrate, I will just look at the following there. When we are integrating that, we can factor out the minus 8 since it's a constant. So we have minus 8 multiplied by the integral from 0 to pi of sine theta d theta. And the integral of sine theta gives us a minus cosine theta. So that we have our result there is minus 8 times minus cosine theta. Then put the limits 0 to pi. And that will simplify to minus 16. So I write my result there is minus 16. Then go on to the next part, the integral of this expression here. So I'll go on and look at that integral there. So we are having the integral from 0 to pi of 16 cosine squared theta sine theta d theta. Factor out the 16 there, and you have 16 multiplied by the integral from 0 to pi of cosine squared theta sine theta d theta. When we are evaluating integrals of this form, if you still recall, it is convenient to use a substitution. So the substitution that we can use there is u is equals to cosine theta. Differentiate this u with respect to theta, and we get the derivative of u with respect to theta is equals to minus sine theta. Then we have our d theta there is minus du sine theta. So when we substitute this into our integral here, it will give us 16 multiplied by the integral from 0 to pi u squared minus du. And we can just rewrite that as minus 16 integral from 0 to pi of u squared du. And the integral of u squared gives us u cubed divided by 3. So therefore our result there is minus 16 u cubed divided by 3, then put the limits 0 to pi. But when we started, the substitution that we used there is u is equals to cosine theta. So substitute that u here, and we'll have minus 16 times cosine cubed theta divided by 3, then put the limits 0 to pi. And the result that we get there is 32 over 3. So I'll go on and write that result there, minus 32 over 3, just because we had a minus sign here. And then when you simplify that, it gives us minus 80 over 3. So this integral there, I'm saying is minus 80 over 3. So that's what we are having now. I will now go on to the next step. Now evaluating the integral on the curve C2 there. So looking at the curve C2, if we are looking at in the counterclockwise direction along C2, we have y is equals to 0. Y is a constant there, it's not changing, so our dy is equals to 0, and x is varying from minus 2 to 2. We are moving in the counterclockwise direction. So the integral along the curve C2 of x squared plus y squared dx minus 2xy dy, it will become the integral from minus 2 to 2 of x squared plus 0 squared dx minus 2x times 0 times 0. This part here, where we're multiplying by 0, just becomes 0. So we remain with the integral from minus 2 to 2 of x squared dx. The integral of x squared gives us x cubed over 3. And then when you put in the limits, minus 2 to 2, it will give us 16 over 3. So we are saying the result for this part here is 16 over 3. Then we add the two values there, and then we have minus 80 over 3 plus 16 over 3. Then we go on and simplify that. The minus 80 over 3 plus 16 over 3, it gives us minus 64 over 3. So that's the result there for the given line integral along the closed curve C.